In this lesson, we're going to look at an application of double integrals, namely determining the mass of a planar lamina. So let's remind ourselves of something from physics. Density equals mass divided by volume. So for example, mass could be written in grams, volume in milliliters or cubic centimeters. So for example, water has the density of 1 gram per cubic centimeter. So if that's the case, then we can solve for mass. Mass then would be density times volume. So this is the first concept we're going to start with, but then we want to talk about a planar lamina. So let's define that term. A planar lamina is thought to be a thin two-dimensional object. If it were really two-dimensional, it would have zero thickness, but we perceive it as a thin two-dimensional object with some very, very small uniform thickness, but it may have variable density. So in essence, it is just some subset of the plane. So let's construct something. We envision this as a piece of sheet metal, if you will, but again, with varying density. Maybe as we move out, it gets more and more dense, it gets more and more dense, kind of heavier, if you will, as we move in that direction. And we would like to know what the mass of this thing is. Well, if we're going to do that, we need to think about what would density be in the case of essentially a two-dimensional object. In that case, the density would be mass divided by area. But again, the density keeps changing. So let's sort of keep that in mind, right? So for a small little piece, if we go to a small enough piece, we assume that the density is essentially the same on that small piece. That would be then the density times the area would be the mass of that very small piece. Well, we mentioned that it has variable density. So the density is changing as x and y are changing. So let's name the density function. And I like to use the letter rho, lowercase rho. So rho of xy is the density function for this lamina. So now what would the mass of this little piece be? The density would be rho of xy at some point xy. And the area is the area of this little rectangle, which would be change in x times change in y. So looking at this, then we would say rho at that point xy or x1, y1, or whatever you want to call it, in that first rectangle. Rho of x1, y1 times the area, which is change in x times the change in y, is the mass of that first area that I just have. We'll call that mass number 1. But imagine how many different little pieces I could make. Could have thousands of them. Each of them will have a different mass because, again, the density changes as we go along. So the total mass would be the sum of all of those pieces. So total mass is the sum of all of those individual pieces. The individual piece, again, was rho at the point x1, y1 in the middle of that little box, times change in x times change in y. Well, you know what we do from there. Then we're going to shrink delta x and delta y to 0 to turn this sum into an integral. So as we do those, doing our Riemann sum, what is that going to give me? The mass will be the double integral over my region R of rho of xy, dx dy or dy dx, whichever order you want to go in. So that'll be our formula for finding the mass of a planar lamina. So let's do a problem. So given the triangular lamina with endpoints 0, 0, 4, 0, and 0, 8, with density function rho of xy equals 3x plus 2y, let's find the mass of that lamina. There's our graph. 0, 0 is here. That's the least dense point. But as we move out and up, it gets more and more dense. So we kind of envision it getting heavier as we head up in that direction. Now, how do we find the mass of this lamina? What do we need to do? We have our formula, right? Our formula is that the mass is the double integral over the region multiplied by the density function times the area change in x, change in y becomes dx dy. I'm going to go ahead and switch the order a little bit here. I'm going to say rho of x, y, dy, dx because I want to go south to north. Not that you have to. So if I start south, what is my equation? Well, the southern border is just the x-axis, so this is y equals 0. How about the northern border? Well, from 8 to 0 is down 8. 0 to 4 is over 4. Negative 8 over 4 is negative 2x. So the slope is negative 2x. Y equals negative 2x. The y-intercept, of course, is 8 plus 8. So my southern border is y equals 0. My northern border is y equals negative 2x plus 8. Now, what does x range from? The lowest x I ever see is 0. The highest x I ever see is 4. So this is what we have to evaluate. So let's do that. Recall the density function, rho of xy is 3x plus 2y, which will give me the following. X from 0 to 4 on the outside, y from 0 to negative 2x plus 8 on the inside. Density function 3x plus 2y. dy dx. And we are ready to do our evaluation. Starting with the inner integral, y goes from 0 to negative 2x plus 8 of 3x plus 2y dy. The antiderivative would be 3xy plus y squared, evaluated from 0 to negative 2x plus 8. Doing our substitution, 3x times negative 2x plus 8 plus negative 2x plus 8 squared. Distributing here, negative 6x squared plus 24x. Squaring this thing, negative 2x times negative 2x, 4x squared. 8 times 8, 64. 8 times negative 2x, negative 16x times 2, negative 32x. Negative 6x squared plus 4x squared is negative 2x squared. Positive 24x here minus 32x would give us minus 8x. And then plus 64 for our inner integral. This was our question, so we'll replace that middle part with our inner integral so that our mass becomes the integral as x goes from 0 to 4 of negative 2x squared inner integral minus 8x plus 64 dx. Antiderivative, negative 2x cubed over 3 minus 4x squared plus 64x evaluated from 0 to 4. Plugging in the 4's for x, negative 2/3 4 cubed minus 4 times 4 squared plus 64 times 4. And the result for that is mass. We don't really have units here to talk about. 149.33 or 448 over 3. Let's do one more problem. We want to find the mass of the lamina defined by that circle, x squared plus y squared equals 16 in the first quadrant with that density function. So we have a circle of radius 4 in that first quadrant. We have our density function, and it gets more dense as it moves out from the origin to the outside. So that's our image that we're going to start with. We showed earlier that the mass of the lamina is a double integral over the region of the density function, dy dx, which I'm going to go ahead and say dA here. So if we're plugging this in, then we get that mass is a double integral over that region of twice the square root of x squared plus y squared dA. And I hope it's obvious that this makes a lot more sense to go ahead and convert to polar coordinates. So let's remember that dA in polar coordinates, which is dy dx in rectangular coordinates, but in polar coordinates are dr d theta. So in terms of setting up my integral, the dA is going to be r dr d theta. We recognize that x squared plus y squared is r squared. So the square root of x squared plus y squared would just be r. Now, what does r range from? What does r range from, and what does theta range from? Well, r goes from 0 to 4. R ranges from 0 to 4. And theta from 0 radians to pi over 2. So that should about do it. Let's go ahead and evaluate that integral. Starting here, and we always like to do the inner integral first. So what is that inner integral? Inner integral from 0 to 4 of 2r squared dr, which is 2r cubed over 3 from 0 to 4, which is 2/3 4 cubed minus 0, which equals 128 over 3. So that's now my inner integral. So plugging that back in over on this side, what do we get? M is integral as theta goes from 0 to pi over 2 of 128 over 3 d theta, which is 128 over 3 theta. Evaluated as theta goes from 0 to pi over 2, which is 128 over 3 times pi over 2 minus 0, which would give me 64 pi over 3.